this class for the neural network part. Now we are going to continue on the neural network or the artificial intelligence method we have covered on the fuzzy logic. Now we are going into the second AI method, which is the neural network. And it is going to be partly slight introduction, and then we will go into details on how to design the neural network in the next class or so. But some of the basics of neural network will be covered in this talk. Of artificial intelligence that includes the fuzzy logic that we have studied so far, and generally any algorithm that utilize the human knowledge to solve any problem in daily activities. We define them as the artificial intelligence method. And as a control engineer, we like to get a controller which sufficiently capture the information regarding the process dynamic and utilize it in the control systems application using whatever method we have, and in this case using the AI method. And the outcome, of course, will reduce the cost objective compared to conventional traditional control engineering approach. This is one of the most important aspects of advanced control, is that we would like to get it to minimize the cost. We like to get it into the optimum region. We like to get it close to the best operation as possible, which is not possible normally using the conventional method or PID method, which is quite drastic sometimes. A lot of changes, variability, and especially for non-linear systems, that would not be very useful method to use the conventional. But for advanced control, non-linear methods, including the AI, is one of the methods that would be able to do what the conventional controller would not be able to do normally. So one of them is AI method, which we have seen before, the fuzzy logic, one method to do it, the different approach, but still under artificial intelligence methods. And then we have the neural network now under another method, which is also under artificial intelligence method, as we will see next. Why we call things intelligent? Because it can speak and express perception, can create creative and be adaptive, can deduce, reason and solve, and hold knowledge and plan and learn. So anything that has all these characteristics is normally called intelligent. The human being have got that. So we are supposed to be intelligent beings if we have that. We don't know what we can call ourselves, but we should be intelligent and be able to do all these things. And that's what the purpose of artificial intelligence is, to get a computer system, computer algorithms that will be able to do these issues. And artificial intelligence has been one of them that has been used, has been tried, and has been designed to be able to do some of it, not everything, but some of it. So this is why we call it artificial intelligence. What's an intelligent controller? Controller that has capabilities to adopt intelligent being ability, those qualities that we've seen. The controller or the software, the algorithm should be able to do that, to have this ability to learn things from what it has seen before. It's able to deduce in the future what is going to happen. Which human beings can do it very well. Again, we have to design a controller that having all this data, all this previous training, it should be able to predict what's going to happen in the future. That's learning. The most important part of what we call artificial intelligence and neural network is to learn things and then be able to deduce things in the future. And adapt, be able to adapt to changes, to disturbances, to new things. It is able to adapt. It's able to find the optimum method or maximum output to be able to design something based on what it has learned before. Learning from learning is able to, so it should be able to adapt to changes, not just standard. And design for only what has been trained. It should be able to be more generalized in that sense. And this is what we call adaptation, which the neural network has got the strong capability of doing so. The other one is the reasoning. Reasoning, or how to reason things. Be able to basically map the input to the output, to reason out. the reasoning is done through the mapping, through the structure of the neural network is able to basically reason out the relationship between the input and the output. And that's again a characteristic of an intelligent being. And artificial intelligence is able to reason out things and be able to come up with a solution for certain things that has not been given before, has not been trained before, something that is more, as I said, generalized. So reasoning out things much cleverly than what other algorithms normally cannot do. Another one is expressing the perception, exactly able to express something or give some perception on something that is already been given. So it's able to map it nicely in terms of nonlinear, the mapping of the input-output, mapping of the disturbance, mapping of the changes, mapping of the parameter changes, mapping of things that are unexpected. So be able to have that intelligent capability slightly, not fully like the human being, but on the side, mapping should be already done by the artificial intelligence algorithm, and the methods should all be done in such a way that is able to do this learn, adapt, reason, and express perception. All it's all tied up to one another, all related to one another. Okay, so on its own, it's coming out all together, and finally, it's able to deduce something based on all this learning, adaptation. It's able to deduce some output again from something that we have not given it before. So if something that has been given before, that's okay, that's easy to be done, and the algorithm can do it. And that's got training, doing the training. But it's something that is not been given before, but with sufficient training. So we need a lot of training data. For neural network, one of the basic conditions is to have good training data so that it is able to deduce well anything that is interpret things that have not been given during the training. So when we have all these abilities, basically we're able to solve the problem in finding the best control action that is required in the control plan. That's the final aim. Yeah, we're able to find the best control action for the control plan in this case using this artificial intelligence method or whatever method that we have designed as artificial intelligence system. So again, to repeat, artificial intelligence, we have few methods, but the most common one is basically the neural network, fuzzy, and genetic. The rule-based expert system has been done before. It's something similar to fuzzy logic. Fuzzy logic also has a rule-based expert, what do you call, functions that you need. Yeah, some of it you see. So there's some overlap in that. But it has been used before. It's a little bit more tedious, a bit more difficult to program, things like that. So it's been used, but not as popular as a fuzzy logic method. So we don't cover it, but if you know fuzzy logic, you can easily deduce the method of using a rule-based expert system. Simple systems, normally we can just use a rule-based as fuzzy logic. If this happened, what happened? If this happened, then what you do? If this happened, what do you do? Okay, those sort of rule-based and little of expert functioning inside that. So that's also an artificial intelligence, but others are fuzzy logic you've studied before, and the neural network we're going to study now, and the genetic algorithm we have touched a bit, I think, in the introduction. We have touched on the genetic algorithm, and that one we have touched. May have time, we may have touched a bit, but if not, we'll cover mainly neural and fuzzy, which is the most popular method. Genetic is also being used in some cases, more towards modeling, but fuzzy and neural network has been used for modeling and control. Genetic algorithm used for a little bit on control in certain cases. It has been used for control system methods. So these are the main artificial intelligence technique of new-based methods. That's the meta-heuristic method, like the ant colony, the particle swarm, and all that algorithm. They put it under meta-heuristic. Some people put it under artificial intelligence. There's got some artificial intelligence, of course, in it. It's basically based on natural findings or natural what do you call phenomena. Some of it is, of course, naturally based. Human beings are intelligent in its own sense. So whatever natural is always intelligent. And this is something that we've learned from from engineering and science, we learn from that natural intelligence to be able to develop all this artificial intelligence technique that happens in many cases, in many applications, not only engineering but in all other applications in the world. The artificial intelligence is being fully used because of its intelligence behavior, intelligence characteristic, intelligence deduction, and so on, which is over the normal method, normal algorithm, normal computer things that what you give, it gives out what you give. But this one, it gives out something that what you have not given, but after you have trained it with things that are given. Okay. Neural network is coming from the natural neural network, which is the brain. The brain is the neural network, the natural one, and this is the one that the artificial neural network borrows its findings from. Okay, but the brain have got all the different characteristics of sensory area, visual association, and auditory, and so on. Whatever you have studied in biology, it's many things, but basically only one part of it that we are using, only one part. How powerful is your brain? Yeah, the natural network. Your brain is a highly God-created system, or you can say your natural organ, which is so powerful, and we are just taking a small part of it to use it for neural network, artificial neural network. We call artificial. It's artificial. So, and that's only the mainly is from the connection from one neurons to another. The connection part to the axon and the synapse is being used in this artificial neural network in the way it has got so many connections. It's got parallel connections, and it's got a very fast connection from one neuron to another that make us be able to function in many ways. So that's that part we are using to create the artificial network, but it's mainly from this basic idea of natural network. Just like fuzzy is also learning from how human being works in deducing and output in the way we think and so on. So that's fuzzy logic, again from natural understanding of the way human being work. Neural network is from how the brain works. It's taking the idea from how the brain works, then we are coming up with this artificial neural network system. In the neural network, we have 3 layers. One is the input layer, one is the hidden layer, and one is the output layer. So we have all these nodes. We call it nodes, just like neurons in the brain. These are called nodes, and in the input nodes, these are the hidden nodes, and these are the output nodes. We can map many hidden layers, but normally we try to minimize to few, and one normally being used. And within the nodes, we have the interconnection, just now in the axon in the brain. So it's connected with one another, and inside it we have the transfer function, and also we have bias extra connections being used to be able to readjust the output in many cases. So bias node 1, bias node for the output layer, and for the hidden layer we have bias nodes. So again, the input layer normally is something standard based on what input we want it to map to the output. So we fix the input, we fix the output, whatever input we want. We decided for the system, for any chemical process, these are the inputs we want to use to control auto model, and these are the outputs we want to output to map. So these are fixed. The one that is not fixed are the hidden layers, which we have to do a little bit by trial and error. There are some methods trying to get the hidden layers by calculation, by standard method, but it's not very accurate. It's the best is anyway the trial and error, which can be done very fast after some experience. You can easily be able to decide on the hidden number of nodes in the hidden layers. And then these are the connections. Within the connections, there are the weights. That's the most important part of the network, the weights. Different connection, different weights. So we will have to optimize the structure and the weights inside this neural network, plus the bias with its own weights. Yeah, on for the bias as well. If you have the bias, not necessarily, it's not compulsory. You may want to use it, but most of the time we have it. But the most important is to get the connections, and these are fully interconnected. So each node is connected to each node here. Each node is connected to each node here. Each node here is connected to each node here. Each node is connected. Also, it's called fully connected neural network. We have partly connected. If you want some to be connected, some to not connected, it's okay, but not an issue, because you can, if you want it to be connected, it's just the weights become zero. Connection is zero. But this is fully connected and is a parallel and feed forward. It's only one-way direction. There's no recurrent of feedback. There is another thought network which is called the recurrent neural network. This is the feed forward, one direction neural network method. So again, as I said before, we will decide on the number of nodes from here and here, and this is what we get with trial and error. And then inside it we have the transfer function, which is also another one that we normally decide, but a little bit of trial and error. Sometimes we have transfer function for this for different nodes we can have, but normally we have same transfer function for this hidden node, same transfer for the output layer. The different can be different transfer function for hidden, can be different transfer function for output. Input, we do not have a transfer function, it's just transmitting input signal to the nodes. So there's no transfer function needed. There's no nothing here, because it's just straight input I1, I2, I3, I4, and so on for the input signals that is coming in to the neural network system here. And so I said again, this is fully connected feed forward, which is the most popular method normally. And how to get the weight, we'll mention later. A method called backpropagation to be able to obtain the weights of the neural network system. So this is the artificial neural network, a small part of that brain, which is the natural neural network. This is the small part that we use, so we call it the artificial neural network system. What we define as the neural network is basically called neural nets, or connectionist model, or parallelly distributed model. The different names normally being used in neural nets, or ANN. And they are systems that are constructed to make use of some of the organizational principles envisioned in the human brain, as we mentioned just now. It's being used using the neurons connection between one neuron to another. We decide on this so-called neural network structure. We call it the structure. Just now we'll see what are the important parts when you design a network. What are the important things that we have to do? And basically, what are the key features? Again, the most important is ability to cope with large volumes of format. So we can put a lot of information into the neural network depending on how many nodes you have. If you have many nodes, then you have a lot more information. You can cope with all those information just like the brain can do. And its ability to learn, again, like the brain can be able to learn once you give the training in learning, and then it will come up with some output when you interpolate in between the learning data that you have. So you need a lot of training data. That's the most important part of neural network. You need the training, sufficient training data, so that you will be able to map the input-output properly. It is also fault tolerant in the sense that because there are so many connections, if any of the connections is not accurate, not strong enough, not up to the accuracy, it can still work, because so many connections, one or two connections doesn't make any difference. That's a very important part of the neural network, of its connectionist, we call it, and the very strong connection between the nodes makes it a very highly tolerant and fault tolerant system. And it's highly parallel, as you can see. One way, parallel altogether, works parallel. This is how the brain works parallelly. And this is one of the most important characteristics of neural network, works parallelly. Just like the brain, the mind, the eyes, the mouth, ears all work together. It doesn't work sequentially, just like computer. You do an algorithm one by one, this first, then the second next, like follow the step by step. This doesn't have step by step, it goes all together in one, which is how your human being works. And this is how the strength of the artificial neural network, it can work all together in one shot. So highly parallel structure is an important feature of AI that makes it very powerful, be able to map very huge information and be able to get an interpolation that is beyond the normal system, normal algorithm, and normal computer programming. And ability to generalize beyond specific. That's again the strength that if you give some data, it's able to interpolate in between. Extrapolate depends, a little bit of extrapolation can be done beyond the training, but normally it has to be within the training data, of course. Something that it does not train before, it may not be able to give. But sometimes it does do a good job, even if it's a bit out of the data, but most of the time it's safe to ask it to interpolate in between the data that you have fed to the neural network, and that is the what you call the strength of the neural network that is able to do that, being able to interpolate very well between the data set, the huge data set that you have. Non-linearly, it can be able to interpolate and give you a good result for both the modeling side and for the control side and for many other applications, which makes a neural network a very powerful method because of this ability to generalize based on its ability to learn well. If you have good data, it can learn. Just like a human being, give some good data, good way of training, it'll be able to understand better. If you give it very little experience and very little case study, it may not be understanding very well. It can understand not so well, but if you give good case study, good data set, good experiences, good previous encounters, you'll be able to understand what is going to do next when something that it has not been given before. Same thing with artificial neural network. If you have those data that is very nonlinear but very rich and make it understand better, you'll be able to predict and generalize much better than without those data sets that you have not given to it. You may be able to still predict. If you do not give enough, then you will have difficulty, not so accurate. You may predict something, but sometimes accurate, sometimes may not be that accurate. So that's important part of the whole neural network is enough data set. Plenty of data set, the better it is for the neural network to work. Different types of neural network models we have in the literature, the linear, the non-linear, cyclic, the recurrent, and within the non-linear we have the cyclic and the recurrent, and the error correcting method or the Hebbian method, not non-error correcting, this error based on the error output, it corrects itself, and so on. So many methods that you can use all on the neural network, depending on what you want to use, but the normal common one that we normally use is the cyclic error correcting passive method, which is the backpropagation training method. The neural use backpropagation is a training method. So this is the common one for modeling and control, but it still can be used for others. If for other sort of applications, we can still use many other methods, and you can see here. But of course, we would like to normally use the non-linear. The linear one, modeling and control, using neural network may not be very effective or may not be very but you can optimize, because you can still use the PID conventional for linear systems. So many other methods for linear. For non-linear, which is difficult to control, then we would take advantage of the neural network and the AI method to be able to map this non-linear system, which is, as I said before, the strength of the AI method or the non-linear method is being able to map non-linear data information, non-linear systems. So basically, it is difficult to be done by the normal conventional. So the common one here we use is this one here. As I said, these are all the people who have developed the backpropagation. Starting from Rosenblatt, Wiedenhoff, and he has come up with the most comprehensive one, Rumelhart, and then new ones. Now the deep learning method, neural network, but whatever it is, the new methods or new deep learning neural network, all is basically coming from the basic backpropagation method. It's only some extra information, extra nodes, extra layers, extra thing added to the neural network that you have the different names. But the basic understanding of node is what we're going to study here. Can still apply to the other method that is using this strategy. The other strategy will have different methods, being able to do the mapping and being able to run the neural network. Then about the three structures basically that you want to decide. First, the microstructure. In each node, what is the characteristic, what is the activation function, which is an important part of each node, to decide that. And the mesostructure is how they are connected, fully connected, one-to-one, parallel, feed forward, or whatever, how the flow of information, how many layers you have, the connection patterns, let's say fully connected and so on. Those are the organization you call it mesostructure, the higher level. The micro one is the lower level characteristics of the neural network inside the nodes itself. Basically inside the node, what we have is the characteristic, the transfer function, which you will see later. There's so many to choose from, but these are the strategy that we would like to use. The microstructure decide microstructure decide micro is the combination of different neural networks and so on, which is not normally important. We normally decide only one feed forward and one neural network. We try to use one network for one application. Sometimes we may add on the new types, new variants, new research we may add on, but that's not a basic issue. That one you can just still use this understanding on what to decide on that one. The highest level microstructure, but mainly the microstructure and the mesostructure that we have to decide for the neural network when we design the neural network strategy. Neural network strategy. This is the topology that we have to decide. Again, the microstructure inside here, the characteristic function, the connection, how they're connected, the mesostructure. And these two things we have to decide for the neural network based on what input and output signal. And the weights here, this output actually, this is not the weight that I didn't show you, but everyone has got its own weights, W1, W2, W3, we have to decide on that. But first of all, we have to decide the structure, how many nodes. As I say, input nodes, we will decide basically on our own requirement. What are the inputs we want to feed to the neural network? That's our own requirement, so we can know that. Output, again, what we want it to map to, what we want it to model, what we want it to control. That's our output signals. And the hidden layer is, again, as I said, this is normally done by the trial and error method, and to decide how many, 4, 5, 6, whatever. Not sometimes we can go certain, but there's a maximum. If we have too many may not be good. You add on another layer. And also the bias node. Bias node is another part of the, like another node basically, but it's basically bias. It's just to top up whatever is not being able to achieve by the neural network here. And then, as I said before, this is the topology where we will decide for neural network when we define the neural network, we define the how many input, middle, output. And in between, we have to tell what is the transfer function for the hidden layers, what is the transfer function for the output layer. It can be the same for both, can be different for both. It can be actually different from each node, but it's not common to do that. So normally we will decide for a certain transfer function, we'll have it the same for each of the hidden layer. For each node in the hidden layer, these are the nodes. This is called the layer itself. This is the layer, this is the layer, these are the nodes. And output we can have different, but normally, as I said, we fix the same here, we fix the same here. And at the input, again, there's no activation, it's just transmitting the signal right into the middle nodes and so on. These are the transfer functions that we would like to use. These are the transfer microstructure, the transfer function that we can normally use for neural network. Yeah, basically the threshold logic, -1 to +1 or 0 to 1. We have the hard limit, -1 to +1 or 0 to 1 in the linear fashion. Basically, there's a linear sort of transfer function. For linear system, we can use this transfer function. Or the sigmoidal, the common one, from -1 to +1 or 0 to 1, which is 1 plus minus e minus x, something like that. Or the tenth function, which is e minus x minus e plus x, e minus x minus e that you can see. So it's common to sigmoidal, coming from what range, from 0 to 1 or from -1 to 1. This is normally the range of data that we would like to get the network to be mapped to. Basically, we have to scale whatever data we have. Normally, we scale between this value of -1 to 1 or 0 to 1, so that we are able to constrain it within the limits of the transfer function. Or we can have the radial basis. Basically, this is, you can see the Gaussian function that we normally commonly see in most of your other applications. So these are the few activation, but there may be others extra one, but this is the basic one, sync model or TANT, as I said, TANH function that can be used as activation function for the neural network design. So this is under microstructure. You have to decide what transfer function you want for the nodes in the middle layer, what transfer function you want in the output layer. As I said, the meso and macro, basically the macro and the meso based on the topology, whether you want a multi-layer feed-forward network as we've seen just now. You can have the single layer laterally connected network type. You can have sort of this traffic light sort of topography organized set of vectors for neural network. You can have the feed-forward method. Or you also have here, you can also have the recurrent signal coming back to the previous layers. So we get recurrent is also common this way, or coming just one signal back. You can have multi-layer cooperative, competitive neural network sort of thing, and hybrid different network structure connected with another different network. So all the different sort of structures you can have, but normally, as I said before, the standard one that we use is normally this multi-layer feed-forward neural network. This is the standard neural network structure that we use for modeling, for control, and so on. It's quite not supposed to say simple, but it's a standard method, fully connected. The training is easy for the neural network, or the recurrent. Some of the things can come back. Here can come back. Okay, so that we'll have sort of a delay function for delete system. For dynamic system, we can use that sort of something called Elman network in the MATLAB toolbox. So these are the topology 6 basic that we can use for neural network design. Go into more detail for, as I said just now, the input variables, and then we have the output variables, and then these are middle layers. In this case, we have two middle layer, one layer here, second middle layer here. This is just a general case, and inputs coming here connected to there, and within this is the weights, okay, and this is output and so on. In terms of every node, this is what's happening. In each node, this is what's happening in each node. Okay, at each node, all the signals are added together, coming from here, from here, from here, from here. Say from this one, coming from here, from here, from here. Just added y1, i2, in, added together. And then it goes to the threshold function, the activation function. You have decided for sigma. This is the equation. It goes through. Okay, the x basically is all the signals coming together. The theta here is the bias one. If you have a bias, it have a function here. If you do not have a bias, then you do not have any function here. So these are the activation function. So it goes to, adds on, and then you process all the inputs through this transfer function. You call it the in this case, the sigmoidal transfer function. Okay, it's a standard way of how each node is being activated, similar for all the nodes. And then the outputs are sent to the other node. So when you get this output is hj, then it's sent to the next node. So this output is sent to the next node, to the next layer. Okay, if it's parallel, fully connected, it will be sent to the next layer. Okay, and each connection, it has its own weight. There is a weight, so it's connection times the weights. Times the weight. These are the inputs coming. So I1 is basically the connection times the weight, output times the weight. I2 is basically the I2 times the weight. Okay, it's an I1 weight, I2 weight, and so on. It's assuming weight is 1, I1 is equals to I1, but the I1 that coming in here is basically the I1 times the weights within this connection. And this is a fully connected parallel and structure and fully basically condensed fully comprehensive neural network, which has got its own strength and so on. And this is the bias, as I said, the theta naught is the bias we add on. Again, I said before, this is not compulsory, alternative. You don't add it, then it becomes 0. So just 1 plus e minus x, whatever is been added on and sum up for it's being activated. So this is your function fx coming out. Okay, so this is a standard way of how each node is being process, each data is being processed in each of the nodes within the neural network structure that we can see here. Backpropagation algorithm, what is it? Is basically this gradient descent to be able to get the weights. These are the weights. The weights, I said before, connected from one to a node to another is being decided. This is the change of weights. How the change of weights for every data set you get, first one data set you get a change of weight, second data, so until all the weights are stabilized and you get a good output. Initially you get input to output will not be right because it's just random. Initially you just randomize the weights. As you go along you improve the weights, optimize the weights through these equations, which you can easily be proven. You can look in the reference literature, ways of improving it, or proving it using gradient descent method. Okay, just the what you call, based on the gradient, we decide on the change of the weights. This gradient descent method, so on. So you change the weights as you go around. First what you call, we can say first epoch, we call it first round, second round, third round, fourth, go on and on until the input and output is close to what we have designed it for. Then basically the weights will not be changing, and then we get the final weights. That's during training, and then in doing testing you may do it again, improve, and then during validate you use that weight and get the output. And that's the final neural network with the weights. The structure with the weights is what the neural network is all about. Okay, the structure, the neural network structure, the topology, which is connections, its nodes, and its weights makes the neural network as it's supposed to be. So, and then basically what they said, this backpropagation algorithm is not the neural network. Some people make mistake calling it an algorithm to optimize the neural network. What neural network? Depending, if parallel, feed forward, or recurrent, or whatever. But those other methods, recurrent, they may have slightly different method of getting the weights. Slightly, because you have a data or you have a connection coming back. So there'll be a slightly different approach, but still anyway, it should be similar in the gradient descent. And of course, this is the simplest method. There are now how to make it faster. This is a slow method, faster method, so they use a better optimization method, Newton's method, conjugate gradient. This is the basically the Liebenberg, the gradient descent, Liebenberg, Marquardt, and so on method, just to improve on the fast, to make it faster. That's all. The results should be more or less the same. One takes a longer time, one takes shorter time, but at the end, if the system has been optimized, the weight is optimized. The neural network structure has been optimized through your good training and good testing method, to good data, to sufficient data, to sufficient excitation of the neural network. You'll be able to get an optimized neural network system that is able to map input output for any other anything that within the data structure, within the minimum maximum data. Cannot go outside that. So you cannot extrapolate very well. If you want it to do too far from the data, you cannot interpolate. Yes, in between. For non-linear system, any non-linear system, it's able to cope for any non-linear system by right. Whenever be able to model according to the mathematical theory, should be able to model any system if you get the structure, you get the methodology right. So basically, what is the backpropagation algorithm? It's a parallelly distributed optimization technique to minimize the error between network and target output by manipulation of the connection weights of the network. So by changing connection weight, you get the network output. So you'll be comparing the network output and target all the time. The error is what you're looking for. The error you minimize until you get error 0 or not 0, certain threshold, which is very small. That means that you have optimized the neural network system. Just like normal optimization technique. Neural network optimization is just like any other optimization technique. The only thing in this method, we are using the technique to be able to get the best weights. You decide the topology, you decide the just now the structure, micro, meso, and so on. Once you get that, then you run the backbone algorithm to get the best weight connection. If still doesn't work, then you have to go back and change something else. We'll see in the next class how you go about. Well, these are the main basic things or you need in the neural network where we're talking in this introduction, are the basic method, basic things, basic issues, basic points that you need to use to design the neural network system for any application, whether it be modeling, control, chemical, electrical, anything. It's a standard way: input, output, and the in the layers. These are the steps you do again, as I mentioned before. Initialize the weight, initialize random the weight first. You don't know what weight, you random it as much as possible. Don't make it fixed in any data. Random it in -5, +5, or something like that. You can use the MATLAB toolbox to randomize. Propagate the signals to the hidden layer. You get the output from the hidden layer, and that you sum the input, and then you get the output as a function, activating function of the summation. You propagate them through the output layer. Yeah, output the next layer. You have the next layer, the next layer. You don't have this output layer straight. You can have many hidden layers. It goes to the same thing, and then goes to the output layer. Same thing. You add on all the signals from different nodes, plus the bias if you want. If you want, this is optional again. As I mentioned again, it's optional. And then the output again function, activation function of the output from that node you're talking about. In this the hidden nodes. This is the output node. F is the activation function. In this case, we call it a sigmoidal. As I said, there are a few activation functions. We're giving a function sigmoidal, but in general, you can use anything. The tanh and what do you call linear activation function or whatever. And then you get error. This is the actual the error output that you want from your data. This is your output from your network. You get the error for all the nodes you have. For all the nodes and all the patterns, you have one data set, you check the error. Another data set, you check the error. So you combine, you summarize the error for all the data, and then you want to minimize the error for not only one data set, for all the data sets, combine them, minimize. Then how to do that? You go to the gradient descent backpropagation algorithm. You adjust the weights again. Okay, once you get the error, you see whether it's within the threshold or not, within the requirement or not, within your whatever you have set. Yeah, okay. If it's yes, that's it. If it's not, then you keep on changing the neural network according to this equation I've shown you before, through the gradient descent method. Change again and repeat again the whole thing, because now you have new weights. W are the weights, and new weights will come up again and keep on iterating this whole thing. These things are iterated again and again until the error is within the criteria or the set that you have decided it to be. This optimization, this is a typical optimization method that you have seen in your other classes, and this is the same thing. Neural network, we are using an optimization method to be able to design it and get it. So it's a repetitive method. Most important also to randomize, not to fix the weight at certain value. If all the same, they're very, very difficult to change. It will not be very much changes. But if you randomize it, then you'll be able to get the weights right at the end. This, as I said, this is a solo method. It takes a long time. It may take 100,000 cycles. Before, when initially you can do 5-10,000 cycles, a long time. But there's a new method. It may take a few hundred cycles and so on. But doesn't matter. At the end of the day, it's mainly to get the weights to be optimized. This weight, the final weight, should be the optimum weight that will be used for the neural network modeling and control. And so, as I repeat for other nodes, this is for one node. It will be done for all the nodes together, parallel. Again, because the whole thing is running parallelly. It's not sequential. It's all one shot. All the nodes are acting together. All the inputs coming in together. The propagation coming together. The output coming together in a parallel online structure method. Not like the sequential algorithm that we have seen in the normal method, normal algorithm, normal computer system, normal thing is just sequential, but this is together we run it to get the best optimized weight for the network using this what we call the backpropagation algorithm that uses the gradient descent method. Basically, what it's telling you is that if you have the strength of the hidden nodes, you don't have the hidden nodes in the initial one that it was designed. It's a bilayer, just input output. It will not be very effective. You can just separate linear data. It can be used for linear system. Good. But with the hidden layers, with many hidden layers and with the interconnection and so on, you can complex linearly separate them linearly, okay, but basically linearly, but the data is maybe non-linear, but you can easily separate them into different regions, or basically model them. Basically, that's what you're saying here. Okay, you can model them well by the more nodes you have, the more hidden layers, of course, but maybe not necessary, maybe too complex. But with the more nodes that you have, the more connections that you have, the more interaction that you have between the nodes, the more connectionist system that you have, you will get a better mapping of the input and the output. This is what it's trying to tell you. The difference between the standard or the simple one and the more complex neural network be able to map this, so it can map more system. Theoretically, it should be mapped any nonlinear system. It should be able to map if you have got the right nodes and activation and topology and do it right, solve rightly. And so that's basically the neural network. And what you can say is that its application is lots. The neural network application is tremendous in all system, in all engineering discipline. Not only in engineering or non-engineering, also can be used not only chemical, in other process systems, in other field, electrical, mechanical. It can be used for many applications, as long as I said before that you need a good data set. The basic condition is that you should be able to get a good data set for the neural network to be able to train it well. And it can be used for classification between a good system, or non-good, acceptable system and non-acceptable, for sort of doing what you can say, the quality control system. For quality control, you can use neural network to decide whether this part is acceptable or non-acceptable. Okay, whether you have what you call this output is reasonable, this output not reasonable, that this got defects or no defects, and so on. So things like that can be used for classification and also for acceptance and quality control and so on. For other systems like in food and so on, it's easily used. Whether you quality of the apples, quality of fruits and all that, you can easily use neural network. For engineering also, you can use it under what we call the classification into different categories of system, and use it for identification, estimation of parameters, partly like modeling, but mainly for parameter estimation of certain parameters in a chemical process system, which is very common, that you use other methods normally, but here we can use neural network to be able to do that, as long as we have the data that will be able to good enough to estimate. Data, I mean, a lot of data, 1, 2, 3 data is not suitable. The more data, such as hundreds or thousands, that will be very best. Of course, you have to map it. Of course, you have to categorize it, and you have to scale them according to the activation function between normally -1 or 0 to 1. But the data is important. Of course, modeling has a lot of usage. We'll see later. We have many chemical process systems that can be modeled using neural network. I mentioned before, mainly we use it for non-linear system, not for linear. Linear system, we have many good linear system available from first principle, but non-linear systems are not available much, so we can use neural network very easily to model non-linear systems, which are normally very, very difficult to model by normal first principle system. Again, fuzzy logic also slightly, we can use it for model, and neural network much better in trying to model things. And also, once we have the model, we can use for control system. Okay, once you have the model input output, the control system is basically the inverse of the input output sort of thing. So once you have a good forward model, you can get the good inverse model, which can be used as a control system, whether for direct control or for indirect control. For using neural network within a modeling of MBC, you use neural network for the model, but another strategy for the control, or you can use it directly for the control, like the inverse model control methods. We'll go through later in this talks, presentations, and will show you how it can be modeled for different systems, and can be used for fault diagnosis, fault detection. Very much commonly used to detect faults. You have data, normal, use standard normalized data, and you give data with faults, then the neural network should be able to tell you, okay, this data has got faults, and which one got faults. So we're able to do fault detection, fault diagnosis in many systems, okay, accurately. Neural network, combination of neural network with fuzzy, I would call it neural fuzzy, combination of neural network with standard methods, and so on and so on. So these are the many applications that we can use for neural network chemical engineering for other systems as well. Mainly we will use for modeling and control. This is the basic part. And the more difficult part for nonlinear system is to use it for the modeling and control of nonlinear system, where normally, as I said before, the models for nonlinear is not easy to get. The parameters are difficult to get. Parameters are unknown. So we can use neural network to model and control. Also, neural network to identify the difficult parameters. That's the good thing about it. Okay, when we use for modeling, we can also use many neural network. Not only one. We can use one neural network for identification. You can use one neural network for estimation. You can use another for the modeling the whole thing. You can use it for control. We can combine with other methods to use for identification. We can combine other methods for the modeling part, and we can use neural network for control. Or you can combine the identification using another method plus neural network for the modeling and so on. So it can be a combination of neural network. It can be a combination of network and neural network and fuzzy logic. We call neural fuzzy or fuzzy neural methods. Can be a hybrid method. Hybrid method is a combination of different methods to achieve certain objective. For example, for modeling, we can combine the neural network with a standard model, standard first principle for the linear part, neural network for the non-linear part, first principle for the linear structure, neural network for the non-linear structure. Okay, first principle for the whole modeling, but neural network just for the parameter estimation also can be done. Okay, neural network for the whole model itself, neural network for the parameters also can, or maybe you want to use fuzzy system together with neural network for this sort of thing. So that's all combination of hybrid systems are the common methods that are being used, especially for research that people are doing now. These are the things that we're working on, not just the standard neural network, but more complex neural network strategy. And now we have what we call now the deep learning and so on that you hear. It's adding more layers, making it more complex, making it more faster, adding more maybe complexity in the nodes, adding more activation function, different from what we have studied, using different methods for optimization. All the different names that are coming in is, but from it's basically from the basic standard structure that I told you, the topology, the connection, the activation function, how you get the weights connecting between one node to another, the interconnection and so on. And at the end, again, depending on the amount of data that you feed in, will decide how good, how optimized, how accurate modeling that you are going to get to neural network or any other method as well, including fuzzy logic. But again, it has to go to certain steps that we'll go to later on. We have to follow. We have to follow the step. We have to follow the way, and then you will get it to work. If you are not able to follow the steps, you just use it blindly, just using you have neural network toolbox, MATLAB, you just use it blindly without going to all these different steps, then you are not going to get a good neural network, not a robust. It can work for that part, the application that you have tried, but for others it will not be able to work. It will work for those data that you have tried, but for other data it will not work. For control, it will work for the nominal data, but for when you have disturbance, noise, everything, it will not work because you have not gone through the basic steps to get the most robust, most generalized neural network that will cover for different changes, different aspects, different actions. Okay, different performance of the system will depend on how good your neural network was designed. You can have a neural network for this type, for this part, but other part you try to use it, you cannot. This is what's happening now. People don't, because you use it blindly, using the toolbox. So you have to understand this principle before you use the toolbox for neural network application. As we will see later, how to go to the methods, what are the methods you have to follow. Just like fuzzy logic, same thing, neural network has to follow this full step. Although you're using the toolbox. Okay, so that's at the end for the first part, and we'll go into the next class. We'll go into a bit more detail on how we are going to go through the steps, what are the steps that we need to follow to make sure, as I said before, we get a robust neural network. Just like the fuzzy logic, again, the neural network have to get the robust neural network. It's very dangerous to use a neural network which is not robust, especially for control. At certain points it will work, in certain point it will not, just fail because it was not robust, it's not general enough. It cannot cater for disturbance, cannot cater for noise, cannot cater for changes in the parameter, which is common in nonlinear systems. You have a lot of changes in parameters and changing all the time, and unless the system controller is robust, we are not able to use it accurately. We are not going to be able to use it confidently, especially in a real online system. In simulation, things may work very well, but when you test it online, which is the test of the day, then it will not work, and that's where artificial intelligence need to be designed properly and not just blindly, properly, and that's why we have these notes of giving you the talks are mainly to decide on how to use the neural network in the most effective manner for modeling and controls of a nonlinear chemical process system, which is very difficult to, very complex nonlinear system, complex plant, complex, even a pH system, which is complex. It's not easy to get the first principle model, but a neural network would be able to do it if you design it properly and well efficient, well managed, and the data set that you've given is good enough. So for that, thank you very much. I think we will have this discussion later in our class. If you have any question, in the next discussion we can discuss on that. Thank you.